Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Time now to get the Bunsen burner and the white coat, because it's time to welcome into the studio the amazing Dr. Dave and Dr. Dom. Good evening.
Hi, Sue.
How are you feeling? So, how is the world of science these days?
I saw an interesting story this week about, actually less hard science, more about people's perceptions of these things, about how much energy things use and how much people think they use. And basically they're finding that people aren't very good at guessing how much energy things use. Things like using an electric clothes dryer, sort of a tumble dryer, uses about 100 times as much energy as using a laptop for an hour.
Really?
And things like that. If you're transporting goods, people seem to think that a truck and a train and a ship all use about the same amount of energy to move a ton of coal around the country, a mile over the country. But actually a truck uses 10 times as much more energy. And a plane, again, another 10 times as much. And the other quite interesting thing was they found is that they did a study of 500 people and they had a look at how well their guesses correlated with different things. And one thing they discovered was that the more people were doing to try and be environmentally friendly, the less good they were at guessing how much energy things use.
That's amazing.
So the kind of people who are doing lots and lots of recycling were actually really, really bad at knowing what was the best thing to do for the environment. And so it should be really important for, if you've got a certain amount of effort you want to spend to be environmentally friendly, you should make sure it's the right thing to be environmentally friendly about. I mean, things which I didn't realise at all, things like the energy used in making a glass bottle and recycling it are actually very similar.
Really?
Whereas an aluminium can, if it's new aluminium, it's almost as bad as a glass bottle. But if you recycle it, then it's about 20 or 30 times less energy than a glass bottle. And so basically glass is a really bad news, which I never really realised.
Being brought up in a pub, but you wanted to return your cases with all the bottles in, and that was the whole thing then. They were always constantly recycled.
Yeah, reusing bottles is great.
Back
so
to the
they
brewery,
go back and not have it. But as soon as you have to melt the glass down, that uses an immense amount of energy, apart from anything else, because the glass bottle's so heavy. So you need to melt a lot of glass.
Let's find out what Dr. Dominic has found out this week that's intrigued him.
Well, I found a fascinating piece of research where astronomers have found a star which is moving at an absolutely phenomenal speed in the Milky Way galaxy. It's moving at 1,000 kilometres per second. Stupid numbers. And if it keeps moving at that speed, it's not going to stay in the galaxy for much longer. It's going to shoot out and become a lonely star, not in any galaxy, just free floating in space. And that's not normally what you expect stars to do. You normally expect stars to live in galaxies with other stars, and it's only a very small number that don't live in galaxies. So what astronomers think has happened is that this star got a bit too close to the black hole which lies at the centre of the galaxy, and it basically got a huge kick as it flew past that black hole, and that shot it off at about 5 times the speed that the sun goes around the centre of the Milky Way galaxy, and it's got enough energy to just fly off and escape the galaxy.
Gosh, how exciting is that? Woohoo! Let's start with a question here that's actually come by email, Dr. Dave, and this has come from Andrea Lewis, who's in Tasmania. Wow, that's a long way away. Good evening to you, Andrea. She says, do you need to leave the atmosphere at a safe angle when you're going to go off in your spaceship?
I think this is because when you're comparing it to if you're re-entering the atmosphere, the problem is if you're re-entering the atmosphere, you're going incredibly fast. Orbital velocity is, I think, order of tens of thousands of miles an hour anyway. And in order to, when you're slowing down, you've got to get rid of all that kinetic energy. You dump it into heat, basically. And if you try and lose that energy too quickly, then you burn up. So if you come in too steeply, you're going to go from the very, very thin atmosphere into the very, very thick atmosphere. You're going to stop very, very quickly and you're going to lose a huge amount of energy. And basically, unless you've got an incredibly well-shielded spaceship, you'll burn up. If you go too gently, you can actually get lift off the surface of the atmosphere and essentially sort of skip and bounce off and carry on. I guess it depends on how much energy you had to start with, whether you'd sort of orbit round and kind of hit the atmosphere somewhere else further around the Earth, or if you're going very, very fast, you could just skip straight off and carry on off into deep space. But if you're leaving the Earth, you've got no issues with a huge amount of kinetic energy. You're just giving yourself kinetic energy with the rocket, and the rocket's very controllable. So as far as I know, you can leave the Earth's atmosphere in any direction.
Yes, I mean, the Earth's atmosphere is very thin. It only goes up to a few tens of kilometres, whereas, say, the space shuttle goes up to about 300-400 kilometres. So it's only on the first 30th of its way up that it's in the atmosphere. And it's not actually getting up to a very high speed in that first part of its trajectory. Whereas when you're coming back, you're actually using the Earth's atmosphere as a brake. So you fly into the atmosphere at full speed. You're going tremendously fast, and you're using that friction with the atmosphere to stop you moving. So you're moving much faster, much lower. And so you have to be very careful how you come in so you don't burn up.
Let's go to the phones now, because we have Mark on the phone from Dunstable. Very good evening to you, Mark.
Hello, Sue. Dr. Sue. Hello, Dr. Dave. How
Dr.
are
Sue.
you?
Yeah, we're fabulous. What's your question,
Good.
darling?
The question is, Dr. Dave, do you think they could ever reconstitute gravity as we know it on Earth? Because I've heard of they get osteomyelitis, and it could take an astro class or astro school where they're trained right from an early age. Yeah.
I think it depends. Certainly people could get much better at manoeuvring in low gravity, I think, by practicing and learning as children. The big problem with being in zero gravity environments is that your body, the way it knows it should grow bone is because there's lots of forces going through those bones. So even just walking around all over the place, there's lots of forces on the bones. So your body has a sort of feedback system, so that if it's not strong enough, it makes a bit more bone there. If it's too strong, then it's a waste of all this weight and bone, so it moves the energy and the resources somewhere else. Whereas in space, you're not standing on, there's no weight there, your bones have very small forces on them most of the time. So everybody thinks, I obviously don't really need these bones, we can make them weaker, make them lighter. And so it slowly sort of dissolves out your bones and they get weaker and weaker and weaker.
That's something that people on the International Space Station, of course, have been looking at, seeing what effect long-term being in low gravity has on the astronauts, and they had to exercise daily in order to stop their bones.
Yeah, they sort of have exercise on great big long elastic bands to try and simulate gravity. I mean, you could simulate something it's not actually simulating gravity on a space station. It would require an immense amount of mass and make it entirely impractical. But you can produce something which is essentially the same thing. Einstein showed that acceleration and gravity are essentially the same thing. So if you've got a big space rocket on your spaceship and you can accelerate at 10 meters per second all the time, then it will just feel like normal gravity. Or if you can spin your spaceship round and round in circles, so in order to go around in a circle, you've got to accelerate. If you accelerate the right amount, it will just feel just like gravity.
Of course, in the film 2001, the spacecraft was rotating, so the centrifugal force would make the astronauts feel something rather like gravity.
All right, well, Steve in Peterborough has called in, and he would like me to ask you this question. He says, when you recharge rechargeable cells, why do they overheat and get hot when they are getting near to full charge? Dave?
It depends. I'm not exactly sure how they're being charged. I can think of various reasons why it might be. Essentially, what's happening is more of the energy which you're putting in from the charger is getting converted to heat, and less of it is getting converted to chemical energy in the battery. While the battery is charging, if it's reasonably efficient, quite a large proportion of the energy which you're putting in gets converted into chemical energy in the chemical reaction in the battery, which can then get released again as soon as you take it out of the charger and plug it into your radio or something. I guess what's actually happening in the batteries as you're charging them is, as you're getting near to full charge, you could well be running out of ions, so basically charged particles in solution in the battery. And as you do that, there's fewer things to carry current through the battery, so the resistance to the battery is going to go up. If your charger is designed to produce a constant current, then it's going to provide a higher and higher voltage. So it's going to put a higher voltage to a higher resistance. That's going to dump more and more energy, and so the battery's going to heat up.
Right, let's go to our email once again now. This has come from Amado Gerardo. What a great name. And it must be in Italy somewhere, I think. It doesn't say. Is air matter? What a great question.
I think that's a question which was definitely quite high up the scientists' ideas about 200 or 300 years ago. Because it's not obvious that air is actual real stuff. It just feels so kind of ethereal and not really there. But air is definitely matter. It has mass. I've measured this myself. If you get a container and pump all the air out of it and weigh it, you get a number. Then as you let the air back in, the air does definitely weigh something. It does have mass.
And of course it exerts forces. If you push on it, you can feel it push back on you. And planes, of course, stay up by pushing air downwards in the air then.
And when you fill your lungs as well.
Yes, yes. So we now know that air is made of gas. It's essentially material which is not stuck together to make a solid or a liquid. The molecules are so far apart that they can just flow freely, so you can walk through it without it getting in your way. But it's a combination of mostly nitrogen gas with a small amount of oxygen and carbon dioxide and traces of other gases. So it's actually mostly nitrogen gas.
Yep.
Good. All right, let's go to email once again. And this one comes from Abraham, who says, what is a projectile?
I think the simple answer is something which has been projected or thrown. So it's basically something which has been thrown. So something moving just under, it hasn't got any forces acting on it other than gravity and a bit of friction. So a bullet's a projectile, a football you've kicked is a projectile. There's also various simplifications which physicists make in order to make their lives easier and make the maths easier. Ideally, that there's no air resistance and everything becomes very easy.
So it's one of those sciencey words then?
It's basically a sciencey word for something which has been thrown.
Dom in Newmarket has said, how do they make caffeine-free Coke? How is the caffeine taken out of it?
The simple answer is by not putting it in there in the first place. Coke is made up of various different things. They won't tell anyone exactly what they put in. It's all supposed to be a big secret. And one of the ingredients is caffeine. So if you want to make caffeine-free cola, all you do is just not put the caffeine in. Getting the caffeine out of something like coffee is a whole other kettle of fish and much more challenging because it's a chemical the plant uses. I think it's actually an insecticide. It's essentially just a poison, and it's a poison with some effects on our brains. Which isn't too lethal to us in small quantities.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. This comes from Dave, who's emailed in, and he said, where does space end?
Well, it's quite a fuzzy boundary between what's space and what's the atmosphere. Most of the weather that we see is actually quite low altitude. It's only a few kilometres up. Now, when people are talking about sending photos into space, traditionally I think 100 kilometres is the threshold where you say you've made it into space. But that's actually a long way above most of the atmosphere, which is only about 10 kilometres or so high.
All right. We've got one here from Steve in Peterborough, and he asks, when I was at school, we used to do a science test in the lab with a test tube and a candle and found 28% oxygen in air. That was in 1959. Are scientists doing tests like this now, and what is the current percentage? Is it about the same figure, or has it gone down?
I think he was measuring something a bit lower than 28. I think it's sort of 21%. I don't think the percentage has gone down significantly. It will vary depending on where you are. You can detect more oxygen if the air has just passed over lots of trees. If the air has just gone through a city, then it's likely to reduced because lots of people have breathed in the air and breathed it out, and lots of coal has been burned and cars have burnt lots of the oxygen, so the oxygen level does go down. On average, over the whole world, I don't know that it's particularly significantly dropped.
What has changed is the carbon dioxide level, and some of the oxygen will have been turned into carbon dioxide, and that's quite worrying for climate change, obviously. But the actual percentage of oxygen won't have changed that much because the fraction of carbon dioxide in the atmosphere is very low. It's less than 1%. And there's many oxygen atoms for every carbon dioxide molecule that you make. And so even if your carbon dioxide levels double, you probably won't detect much of a difference in your oxygen level.
Now then, we've got one on email here that's come through from Robbo and the Chimp in Burnham on Crouch. which is nice. And it says, "Hi Sue, Dr. Dave, Dr. Dom. I have what may be perceived as a silly or even an irrelevant question, but it's all right, we don't mind." He asks, can water float?
The simple answer is yes. If you think about a lump of water in the top of a bucket, what's stopping it falling to the bottom of the bucket?
The water.
The water around it.
Right.
Every lump of water in the bucket is floating on the water around it. So water is always floating. But because it's the same density as the water around it, it doesn't move upwards or downwards. It doesn't rearrange itself. If you have water of different densities, if you've got hot water, it will float on cold water and you can create a convection current. So hot water over an underwater volcano or something will float upwards and you'll get an upwelling of hot water from over the volcano. Cold water sinks. So near the North Pole, water is cooled down because it's very cold up there. And it also gets a bit more salty because as water freezes, the salt isn't taken into the ice. So the water gets more salty. And that sinks downwards, and then warm, less salty water from other places floats upwards. And so lumps of water float on top of each other and sink under them all over the place. Sort of not very salty water enters the Mediterranean, and it floats on top of the much saltier water where lots of evaporation has gone on, which leaves the Mediterranean underneath it. So yeah, water can float, and it does all the time.
Excellent. Let's go now to this one. Jill has called in, and she says she wants to know about Chinese lanterns that fly over. And of course, this time of year, everybody's letting them off at festivals and things like that. But are they dangerous when they come down, having a naked flame, for instance, or are they biodegradable? What happens?
I think these days they're mostly made of paper so that they do biodegrade. And I'm not sure whether the flame tends to go out before they come down. I would imagine that it's the fire going out that actually stops the lantern from floating as it comes down.
I think you're right, as long as nothing goes wrong, and if the whole thing catches fire, which I think does happen occasionally, then it could fall down much sooner than it would do otherwise. And yes, you're essentially then dropping a large candle somewhere around the countryside, and if it's very, very dry, there's no reason why that couldn't start a fire.
I think the fire is quite small, and you'd have to really be quite careless to have it land on your head and actually do you much harm.
All right, let's go to this one here. Ahmed from London has called in. If you removed the core in the Earth and made a hole from the North Pole to the South Pole and you jumped into it, what would happen regards gravity?
Well, that would be quite exciting, actually. You would fall down to the centre of the Earth. And at the centre of the Earth, there would actually be no force on you whatsoever, because the gravitational force from all the different parts of the Earth would be pulling you equally in different directions, and it would all cancel out. But you'd keep moving because you'd fallen down, you got some velocity, and you would just reach the other side of the Earth. And there was
no air resistance.
If there was no air resistance.
Physicist approximation.
Absolutely. If there was no air resistance, you would fall and just peek out the other side, assuming the altitude of whatever's on the other side is exactly the same. You would just stop there, and then you would fall back through your hole and come back, and your velocity would be nothing. When you came back, you'd be moving fastest when you moved through the centre, even though you wouldn't feel any force at that point.
I guess as long as there's no effects from any gravity from the moon or other planets or the sun, at which I don't know whether they could possibly pull you off your route at all.
Yeah, I think that would be difficult. And actually the rotation of the Earth would be quite unpleasant, because when you jumped off the surface of the Earth, you'd be moving with the surface of the Earth, which is rotating. And so actually you wouldn't go vertically downward, you would go down in a slant.
I guess this is why he was suggesting doing it from the North Pole, because otherwise you would
north to
spiral
south.
down.
Yeah.
Yes, you find yourself rotating, but not slanting.
All right, well, you do some dangerous things, you two, don't you? That's a lovely one. We've got a question that's come in from Susie, and she just simply asks, as a lady of a certain age, I buy products that say things like multi-layer cell strengthening or lotions and potions that will get rid of wrinkles, double chins, age spots, and the list goes on. The prices range from cheap to very, very expensive. Really, she says, my question was, do these products really work with the ageing process?
I don't know. I certainly haven't heard of any good evidence that any of them are hugely more effective than anything other than just general moisturisation and a few odds and ends. At some point, probably someone will invent something which is effective, which will be slightly depressing for me in a strange kind of way. But
we're all young on this programme.
I think the main tricks are to avoid the things which do encourage the aging, speed up the aging process. So things like smoking is very, very bad. That releases all sorts of nasty toxins into your body, which will speed things up. And the sun, similarly, ultraviolet light can damage your skin. But other than that, I certainly don't have any answers which other people don't.
Now, Dr. Dom, I think this could be one for you, actually. This is about asteroids, and it's John, who's in London, who says, is there any truth in ancient recorded text that the Earth will be hit by an asteroid in either 2012 or 2015? So what do you reckon, Dr. Dom?
Asteroids certainly do hit the Earth periodically. The latest big asteroid to have hit the Earth was in 1908. Luckily in Siberia, where not very many people live, and so actually it went largely unrecorded until explorers found this large devastated area where they thought something must have hit. And we think that possibly it was some kind of rock which did for the dinosaurs by colliding with the Earth 65 million years ago and causing a mass extinction back then. It's quite unlikely that there would be a large impact in the next few years, because recently astronomers have started cataloguing pieces of space rock in the solar system, working out what the orbits of those space rocks are and working out whether they pose a threat. And there are a few which may pass close to us, but none of them which look set to actually collide with us. So we can say fairly confidently it's quite unlikely that there will be any collisions in the next 10 years or so. Hopefully, if something was going to collide with us, we would have a few years' warning, and then we could start thinking about what to do to get rid of it, whether you could fire a nuclear missile at it. Actually, firing a nuclear missile at an asteroid coming your way is not such a good idea, because you just break it up into lots of tiny pieces, and then those pieces all hit you and can cause a lot of damage, and then they're radioactive as well. Possibly one idea would be to throw lumps of, say, copper at this asteroid, and that might deflect its path so it didn't hit us. Something very heavy, basically, just to give it a push and change its orbit.
All right, this one here is from David in Suffolk. He says, I have about 20 cacti and I wondered why they have spines on them and why they don't require a massive amount of water, like other plants.
Cacti are absolutely fascinating things. The reason why a plant uses up lots and lots of water isn't because it likes drinking or it's particularly using that water. Most of the water which plants use is actually just wasted. What the plant is trying to do is taking carbon dioxide from the atmosphere, use sunlight to react with a little bit of water, but not very much, and convert it into sugar. But while it's doing that, it has to have lots of open pores in its skin to let the carbon dioxide get in. And if it's hot and if it's dry, that means that it's letting lots of warm, damp, moist cells be exposed to the air from outside. That causes lots of water to evaporate. So a sort of byproduct of carbon dioxide coming in is lots of water going out. One really cunning thing which cacti do, which I've only found out quite recently, is that what they do is, one way they preserve water, there's all sorts of other ways, but one of the major ones is they only open the pores, the stomata in their skin when it's at night time, so when it's much cooler, so there's much less evaporation. So what they do is they open the pores at night time, they absorb as much carbon dioxide as they can. Then, as soon as it starts to warm up in the day, they shut all of the pores, which locks all the water inside. They then use what the little carbon dioxide they've managed to absorb, they photosynthesize with. Once they've run out of that, they just sit there and wait until it's night and it cools down again. They open the pores. So they basically save a huge amount of water by only opening their pores when it's at night time and when it's cold.
And of course, that's why cacti grows so slowly. They're using the water to grow, and they don't have much water, so they only try and grow quite slowly.
Yeah, and they can only photosynthesize for maybe half an hour every day, so they don't use very much water. And of course, that's why they're so desperate to keep hold of all the growth they've got and don't let animals eat it, which is why they're so spiky, to try and stop the animals eating them.
Don't eat me, I'm growing slowly.
Yes.
All right. Cacti, very clever stuff. We've got one here that is from Richard in Great Yarmouth. Can you ask, how big is the universe? Do they think there are other types of life forms apart from carbon-based? From Richard in Great Yarmouth.
Well, we can actually guess the size of the universe quite accurately to be about 13.6 billion light years across. And that's because we know that the universe is expanding, and we can look at how fast it's expanding. And we think that the universe came out of the Big Bang 13.6 billion light years ago. So the bits on the outermost edge of the universe travelling at the speed of light have been able to travel 13.6 billion light years. In terms of there being life elsewhere in the universe, well, there are about 100 billion stars in each galaxy, and there are about 100 billion galaxies in the universe. So that's a huge number of stars, any one of which could potentially have a planet orbiting it that could have life. The problem is we don't know how difficult it is to form life. We know it's quite easy to form the molecules that life forms from, the amino acids for sugars. We've detected those on comets, and we think that solar ultraviolet radiation can bring those molecules together. We don't know how those molecules come together to actually form the first microbes, the first bacteria, and that's a real problem.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.